And it's a real honor to be here, particularly given the role Chris Flutis played in setting up the Energy Institute here and creating this lecture series. He was a friend and colleague in chemical engineering, and certainly a giant and a visionary in chemical engineering and in energy, and is sorely missed, as I'm sure you all feel here at Texas A&M. But it's an honor to be part of this and part of the external advisory board here at Texas A&M. So Strato said that what I'd like to talk to you about today is the future of solar energy. And I do this as an illustration of some of the work we do at the MITEI Energy Initiative in what we call outreach. I've noticed actually in the visit here today lots of similarities in objectives and goals of the Energy Initiative at MIT and what's done here at Texas A&M's Energy Institute. We do research, we do education, we do outreach. And in part of the outreach work we do, we work to bring together multidisciplinary teams of faculty in technology and economics and policy areas who can help us understand issues in moving forward key technology areas to meet the energy challenges of the future. In particular, I think we understand that there's a dual challenge that we face ahead of us globally. And on the one hand, we need to provide more energy to the people of the world, particularly driven by developing countries. As standards of living increase, as population increases, how do we bring more energy to people who need it to improve their lives? At the same time, it's clear that we need to reduce emissions of greenhouse gases from the energy system. So how do we do those things together? How do we both provide more energy and remove CO2 emissions and other greenhouse gas emissions from the energy system? So we started looking actually a little bit more than a decade ago at what we see as potentially key technologies in getting us to this future 2050 and beyond, where we'll live in a world where more energy is needed, and at the same time we need to have less carbon emissions in the system. And we began with a study on the future of nuclear power. That's the only zero carbon energy technology we've ever practiced at scale on the planet. We've done studies on the future of geothermal, the study of coal, so coal plus CCS, natural gas, looking at the opportunities for fracking and fuel switching opportunities. The most recent study we did is this one on the future of solar energy, and that's the one I thought it would be interesting to talk to you about today. So we're looking at this dual challenge: more energy, less greenhouse gas emissions in the system. And as a way to think about this, imagine and look at the possibilities of generating perhaps 50 times as much solar energy by 2050 as we do today. So we're around 1% or so globally today in the electricity sector. Can we get to something like 50 times that by 2050? And if so, what would it take to get there by way of technology improvements and accompanying policy options? Solar energy is obviously a very attractive technology for meeting these challenges going forward. Among other things, the scale of availability of solar energy, it's here in great abundance relative to our energy needs, and its broad distribution across the globe make it an attractive source. So the map here, you've seen maps like this, I'm sure many times, but looking at solar insolation across the globe, and you can see wide latitude ranges over which there's abundant solar resource. And in many of those regions, we haven't actually tapped solar to the degree that would be beneficial. Ironically, we've done a lot more solar development in some cases in high latitudes where solar resource is not so good. As an example of the scale at which solar is available, I have a number here at the bottom that cites the land need for solar in the U.S. If you took half the land we use to grow corn that's used for corn ethanol today, that could supply all of the U.S.'s electricity with today's solar technology. Right? So there's obviously a big resource available for us to use. In this study, we focused on solar to electricity. There are other things you could look at. You could look at solar to hot water. That's a very economical way to use solar in many parts of the world. But just to focus, let's look at electricity production. And we looked at then two major technologies that are involved in solar electricity production. The first one of those, probably the most common that you see around, is solar photovoltaics, or solar PV. That's what you see on rooftops around many neighborhoods or in large utility scale installations. It is by far the most common implementation of solar electricity production today. It accounts for some 97% of global solar development to this point, solar capacity, about 200 gigawatts. One of the virtues of solar PV is that it's modular. So if you look at one of these solar modules, one of the little rectangular sections here, what you learn about its efficiency, its behavior in a given environment scales very easily just by replicating. All right, so there's not much mystery to scale up with PV. And that makes it very easy to do fairly affordable research on the systems and then scale up. The other technology of interest is so-called concentrated solar power, or CSP, sometimes called concentrated solar thermal power, because it uses a thermal electricity production technology. You use a steam turbine, for example, to produce electricity. The idea is illustrated here by a set of mirrors or a heliostat field. This array of mirrors is used to focus sunlight up onto a receiver. The receiver is used to focus that light and heat up a working fluid or a heat transfer fluid. Now, with that heat, we can then produce steam to drive a turbine for electricity production. Because there's, in most implementations of CSP, there's a turbine involved, it generally needs to be done at large scale to be economical. And so you don't see rooftop applications in CSP. You see it in utility scale installations, generally in the desert. Unlike PV then, capital cost is an issue. You need to build large utility scale systems. We don't know nearly as much about how CSP scales because it's not as modular as PV. Unlike PV, it needs clear skies. Hazy skies don't work. You need to have direct normal irradiation to focus light onto a receiver. Whereas PV works okay if there are hazy skies or if there is humidity in the air. It has one big advantage over PV in that although PV only makes electricity when the sun is shining, CSP is easily made dispatchable. That is, it's really easy to integrate storage into CSP. And we'll talk a little bit about how to do that a little bit later on. So those are the two technologies that we're going to talk about. So I'm going to talk in this first segment of the talk, I'm going to about where do we stand today in solar electricity production, how much penetration is there globally, and what are some of the challenges that are in front of us. And then I'm going to talk about three main messages from the study done, and those will have to do with technologies to focus on going forward. What are some of the technology challenges, a message about the system, the energy system into which we need to integrate solar, and what are some of the challenges that are already beginning to appear there. And then thirdly, what are some of the policy issues in front of us that will affect how readily we can scale up solar as part of our energy system. So a brief look at where we stand today in solar technology. This is a look at PV generation capacity in the U.S. and its growth over the last 8 years or so. Going back to 2008 up to 2015. And by 2015, you can see that we had some 7 gigawatts of solar capacity in the U.S. In cumulative capacity by 2015, we have the distribution across states that's shown on the right side over here. And in that, you can see that there's a very broad distribution across states. California, which has, as you can imagine, a great solar resource. The largest amount, perhaps more baffling, is that there is more solar in Massachusetts than in Texas. Go figure that one out. If we look at growth in both wind and solar, so this is the growth in renewables is certainly not restricted to solar. In fact, wind has certainly grown more rapidly here in Texas than has solar, as it has around the world. So this looks at global wind and solar installed capacity. Between 2006 and 2015, you can see some 562 gigawatts of new installed capacity. By 2015, global installed capacity for solar PV is about 215 gigawatts, maybe 415 gigawatts of wind, for a total of about 630 gigawatts. So very substantial amounts of both solar and wind, and rapidly accelerating in installation. What drives that is, of course, decreasing costs of solar. This is a look at PPAs that have been signed between about 2007 and today. These PPAs are power purchase agreements. Those are commitments of utilities to buy electricity from a generator. In this case, we look at a variety of solar installations across 5 regions in the U.S. And you can see a decrease in PPA price of order 50% over the last 5 years or so. And in all of the regions here, we're down to less than $50 per megawatt hour, with the exception of the Midwest, where PPAs are less than $60 a megawatt hour. So less than 6 cents a kilowatt hour in all of these regions. The lowest cost PPA in the U.S. that I'm aware of so far is one that Nevada Power signed back in 2015, August of 2015, at 34 cents, 3.4 cents a kilowatt hour. So very cheap. This is the U.S. Globally, you see similar results. In 2015, there were PPAs signed in Chile and Peru for less than $50 a megawatt hour. The lowest price I know of globally is Dubai at 2.9 cents a kilowatt hour. I got to say, I don't think anybody can make electricity with solar at 2.9 cents a kilowatt hour. I think the bid there is based on the expectation that cost will drop 2 years from now when they actually have to build the plant. So there's a bet going on in that PPA. Solar economics are looking competitive relative to other energy sources. This is a look at solar compared with natural gas power production. So I put natural gas over here on the far left, giving a range. So the light green bar running horizontally across is to represent a range of natural gas-fired electricity prices. At the low end, natural gas combined cycle power plants with a low price of maybe $60 per megawatt hour, with regional variations up to maybe $76 a megawatt hour. More expensive would be gas turbine, electricity generation for peakers, ranging up to maybe $123 a megawatt hour. But so that defines the 60 up to 123 defines this bar for natural gas powered electricity. To compare that with estimates or values for solar, these are from our future solar study, they're 2014 numbers, which look at different kinds of solar installations in different parts of the U.S. Right, so comparing, for example, utility scale PV in California. So utility scale, as you'll see, is the cheapest way to do solar PV. California is the best solar resource that we're exploiting right now in the U.S. And there you get a cost for electricity of about $105 per megawatt. After the investment tax credit, that comes down to about 60, right? So pretty comparable, 70, excuse me, pretty comparable to NGCC power after the tax subsidy. At the other extreme for solar electricity costs in the U.S., actually it's not the extreme, but it's a much higher cost, is a less economical mode for building PV, which is residential scale, so rooftop solar done in an area, Massachusetts, without a very good solar resource. And not surprisingly, electricity there is much more expensive at $287 a megawatt hour. And after the investment tax credit, that comes down substantially, but comes down 30%. But you still are well above the highest price for competitive natural gas, right? So residential PV is not going to compete well in a state like Massachusetts with natural gas-fired power. These were 2014 values. If you look out at 2017 CapEx estimates, give us cost for PV of $1.25 a watt installed, and for residential about $2.80 a watt. All right, so PV is becoming more competitive with natural gas, and in utility scale in California, you'll be down competing well with natural gas, with some provisos that will come here in a minute. That trend has been driven primarily by the decreasing cost of solar modules. The expansion of silicon wafer technology capacity in China about a decade ago has had a profound impact on the cost of solar PV manufacturing. And you can see that for both, well, you can see that in the light green curve, the module price has dropped about 85% over the last 8 years, from 2008 out to today, but appears to have pretty nearly leveled off. You'll also see that the price of utility scale PV, so installed, has also dropped significantly, as has residential scale. But those two curves are more or less parallel to the module decrease, which tells you that all the other costs involved in solar electricity generation are not going down so much, right? And those other costs are what get swept under the label of balance of system costs, right? And so increasingly the cost of solar electricity for PV is dominated by these so-called balance of system costs. So these are what the balance of system costs look like. what's entailed in those. For utility scale PV, you can see the module cost is the same for residential or PV. But then we have to include costs for power electronics, so the inverter, for example, and any amplifiers. We have engineering construction costs, taxes, and then there's margin and G&A costs, right? And you rack all those up to get up to the total cost of electricity, utility scale electricity. For residential scale, same set of items, inverter, other hardware. Installation costs are much more expensive because you generally have to do this manually. Silicon is glass. The glass is heavy. You have these units to lift up onto the roof. And so the installation cost here is much higher than in the utility scale case. The customer acquisition is more expensive. That's something you don't generally have to deal with in utility scale, tax, and then margins out here. So you end up with a much higher final cost for the electricity. So those are challenges to deal with going forward with PV technology. Another challenge here is an intrinsic system challenge, which relates to the fact that solar PV is not a dispatchable energy source, right? So solar PV panels make electricity for you when the sun is shining. The sun goes down, they quit making electricity. What that means is that as you add more and more solar PV into the electricity system, you'll be generating more and more electricity midday. You have zero fuel cost with solar PV, so you'll be generating and selling into the system more and more zero marginal cost electricity, right? And what does that mean to the overall system? Well, it's going to end up driving down the average market price as solar penetration increases. Worse is that the value of the solar asset to the asset owner is going to decrease dramatically, because what you get back selling in at these low costs midday is going to reimburse you less and less as solar penetration increases. So that's a big system issue to deal with, and that's, of course, very tightly coupled to the fact that we don't have adequate storage solutions today to couple with PV. So with that quick background survey on where we stand today with PV, we want to look at what do we need to do to make this PV scalable and affordable in meeting global energy needs. And so we're going to focus on three main messages, as I said. The first of those is technology approaches and what do we need to do in an R&D agenda to get us where we need to go. Primarily there, the focus is on developing transformative technologies that can produce dramatic results, reductions in overall system costs. So we've got the module cost down substantially, but we need to get the overall system cost down for technology like solar. Second message is that we need to prepare for greater penetration of PV. As illustrated by that previous slide, we need to have, for example, more storage available to enable solar penetration at higher percentages. And then last of all, we need to look at how do we support solar deployment with most efficient policies to get the most solar generation we can for each dollar of support that we spend. So first, I'll talk about focusing on transformative technologies and how those might reduce system cost. And I'll start with an observation that I'm going to focus on non-silicon-based technologies for the simple reason that I think the private sector already has the incentives it needs to improve silicon-based technologies and associated balance of system costs. It's a well-developed technology. As you've seen, we're well along the pathway to deployment of silicon-based systems. Silicon is going to be the dominant technology for a decade or more down the road. But I think there's substantial economic incentive for the current industry to carry that load. So places like Texas A&M or MIT or other basic research centers need to look at how do we develop emerging technologies that can potentially dramatically reduce overall system costs. So this is where we are today. We have these PV technologies that are made out of silicon, crystalline silicon, that are efficient, they're reliable, they're robust, quite durable. We have a very abundant raw material resource, and they're non-toxic. But they involve thick wafers, and that results in very heavy systems that are rigid. And as you saw or I mentioned, that results in very expensive installation costs in residential systems. And there's also a complex manufacturing process. The wafer manufacturing process for silicon is very energy intensive and very capital intensive. So this has a lot of intrinsic characteristics that we think can limit its scalability to this 50% penetration, say, into a global electricity market. So what might we do? An interesting observation is that there may be great potential in looking at more complex molecules to serve as PV materials, simply because even though they're more complex molecules, they're in many cases simpler to synthesize, and they result in formats that could be much easier and much cheaper to install. So, for example, instead of looking at crystalline silicon, if we move to the far right here, in what I call emerging thin film technologies, materials like perovskites have gotten a lot of interest lately, primarily because we've seen unprecedented improvement in efficiency in a very short amount of time. Perovskites, we just started to look at perovskites globally as a PV material about maybe 5 or 6 years ago, and have gone from a couple of percent efficiency to over 20% efficiency in that 5 or 6 year period, which is phenomenal. On the bad side, perovskites don't last very long. They perform at that 20+% efficiency level for maybe a couple of hours, right? So there's not a commercial opportunity there yet, but figuring out how to make them more durable and environmentally sustainable is a really important issue. There are other organic systems or dye-sensitized solar cells or quantum dot systems that also offer great potential for lightweight, low-cost manufacturing. These are some of the potential technology or system improvements you could get out of these systems. You can make these into very light and flexible thin films. This is one of these solar films on a piece of hair to give you a sense of the scale of thickness there. These can be produced through high throughput processes, high throughput printing processes to do these very cheaply, very fast, and with a very small spatial footprint. Many of these systems use very abundant raw materials. Illustrate that here with sulfur, which goes into some of these the systems. And potentially they could be made into large format films, which could be rolled out in large structures. This is not PV here. This is quite the opposite. It's a tarp to cover Fenway Park just before a rainstorm. So there's a lot of potential here, but there are also big challenges. Right now, these are perovskites notwithstanding. Most of these are very low efficiency materials. Most of them have very low stability, and all of them are unproven at scale. Right, so there's a lot of work that needs to be done there. We can do many of these already, though. We can print some of these PV materials in a way that's quite durable. This is a PV material we've printed at MIT. This has been run through a laser printer. After the PV was made, it works just fine after a laser printer. This is a very lightweight PV cell, which was made by first synthesizing a polymer film of parylene and then depositing the PV material on it. It's a very, very thin, lightweight system. This is the PV material being floated on top of a soap bubble. Give you a sense of, I don't suggest soap bubbles as an infrastructure support here, but that's how light it can be. So this is a look at some of the ways in which these new thin film materials could lower balance of system cost. One of the issues with what are called commercial thin films today is that some of the materials that are used are in rare supply. So for example, CAD-TEL systems that are sold by First Solar are very nice systems, very cheap solar PV systems, but they use cadmium and tellurium. If I wanted to scale those up, a CAD-TEL system up to 50% global electricity needs by 2050, I would need the tellurium that I would need for that would require me at today's production rates about 1,400 years, right? So that's a non-starter. So we're looking for thin film materials which can be done or obtained from abundant raw materials. This is a look then at materials like sulfur, which is in CZTS systems, which has a very abundant supply on Earth. It would take about 6 hours of sulfur production at today's rates to meet 50% electricity needs in 2050 in a CZTS system. So there's a lot of some of these materials around. The other technology I wanted to mention is this concentrated solar power technology, which has also some interesting R&D possibilities. I just spent a minute on sort of the flow chart for CSP, just to point out where the opportunities are. So in concentrated solar power, as I mentioned earlier, you take this incident solar energy, you focus it with mirrors on a receiver, at which you absorb the heat, usually into a heat transfer fluid. Today, we typically use molten salts to do that at just a little less than 600 degrees centigrade. One way to improve the efficiency of these systems would be to increase the temperature to which those salts are stable. So higher temperature systems would be useful in CSP. Secondly, we take some of that energy and we use that to create steam or to heat up some working fluid to drive a turbine. There's an efficiency loss there, which is on the order of 35. You get an efficiency of about 35% in producing electricity. If I could go to higher temperatures there, or if I could go to alternative power cycles, I could conceivably increase the efficiency in that. So again, the need to go to higher temperature systems. In addition, between these steps, there's the opportunity to store the energy. So before, I don't have to take this hot fluid and immediately use it to produce steam for electricity. I can take some or all of that hot fluid and shuttle it off to an insulated tank and just let it sit there until I need electricity. Right? When I need electricity, I bring it back out and I heat exchange it against water and make steam to produce electricity. Round-trip efficiency on that thermal storage is better than 97%. Right? So it's really efficient storage, and it's not high-tech storage. And it's because you've done that before the big loss in this process, which is the power generation itself in the turbine. It turns out that in these CSP systems, the more storage you put in, up to a point, turns out in tower systems up to about 18 hours, the more storage you put in, the lower the cost, the levelized cost of electricity, which is because you end up using the turbine more and more hours a day. You can get capacity factors up north of 70% on these systems. All right? So there's integrated storage here that's possible, and we need more research on that. So there are plenty of opportunities in CSP to improve the overall cost of the system. This is an example of a new way to approach CSP that might be useful going forward. In this system, instead of focusing on a tower, so a heat exchanger directly, you beam solar energy into a bath of a molten salt. So rather than absorbing the energy on the surface of a metal and subjecting that metal to extreme thermal fluctuations as the sun comes and goes, you absorb the energy over a couple of meters of depth in this bath of a molten salt. You can then have that molten salt serve as a reservoir for heat exchange against water for making electricity any time of day or night. And that looks like a way to do this at much higher temperatures since I avoid the thermal stresses on the heat exchangers for absorbing and may provide a pathway to much more efficient CSP. This is an idea for a more efficient power cycle on the back end. This is a combined open-air Brayton cycle with a natural gas peaking capacity. The idea here is to heat exchange compressed air against this molten salt in a multi-stage turbine. In the final stage of the turbine, you can vary the power output of the system by directly injecting natural gas, since at that point you're above the auto-ignition temperature of the gas. So you can get variable power output. And it may be that a system like this CSP, since it's using a turbine, would provide you a way to migrate over decades from a natural gas-dominated power system to a solar power electricity system. So that was the agenda, or a possible agenda, for CSP and for PV going forward. So the second message that I wanted to talk about is how do we prepare for greater generation of PV in the electric system. And again, I'll say that because we've got so much experience with silicon PV systems, I think we can be sure that that's going to be the dominant technology, at least for the next couple of decades. But the very large-scale reliance on PV is going to give us some severe system challenges in integrating solar into the system because of its lack of dispatchability. And we want to look at the issues there. And then lastly, we need to deal with issues of some of the policies for retail electricity pricing and problems and challenges that may produce in the system by way of consumer resistance to PV. So an example of the system challenge that I was talking about. Again, in a world without storage, which is fundamentally where we are today with solar energy, what does a dispatch curve look like for, or a typical load curve look like over a 24-hour period? This is a simulation for ERCOT, so this is local. And it's a look at generation for different levels of penetration of PV. This far left curve is 12% penetration of PV, and then we go out on the right to 58% PV, right? So at that point, lots of PV. First observation is that this very top curve here, the black curve on top of all this, is the overall load in the system. Before you have any PV, all of that load is produced by non-solar generation, right? And non-solar generation in these curves is the brown piece, right? When I put in 12% solar, that displaces the non-solar generation midday when the sun is shining, right? And so it brings down the peak need for the non-solar generation, right? So you notice that the capacity of non-solar generation goes down from maybe 76 to 70%, or 70 gigawatts rather, okay? When I go to higher levels of solar penetration, interestingly, that capacity of non-solar generation doesn't go down anymore, right? So you can't get rid of a lot of the other generation capacity simply because without storage, I'm not able to meet the needs off of the peak solar time of day with the solar generation. So as I increase solar more and more, I get more and more solar in this middle part of the day. It displaces more and more of the non-solar generation right around midday, right? But that leaves me with the same non-solar capacity needs, and it gives me a bigger ramping requirement than I'm going to need. So I'm going to have some system challenges to deal with if I don't have storage met for these systems. Storage needs are also illustrated by this plot, which looks at the solar resource for each 24-hour period for every day in a year. This particular plot is in Golden, Colorado. That's where NREL is. And they have lots of good data there on their solar resource. And so you'll see that in January or any one of these days, you see where the little black parabola, more or less in the middle of the day, that's where the sun comes up and you get a solar resource. So there's a gap between the little black parabolas going from day to night and day to day. You'll notice that in January, the little black sections aren't so big, whereas in the summer, May, June, July, August, there's a lot of dark there, so there's a lot of solar resource when the days are longer. You'll also notice that even in good solar resource seasons like May, there are some days that are cloudy and you don't get a good solar resource. So solar is fairly repeatable. That is, you understand day to day what the variations look like, but there's clearly a need for day-night storage, and there's going to be a need for seasonal storage to get from times of year like summer when I have a good solar resource, to times of year like January or December when I don't have much solar resource, right? So that's a challenge we need to get to address with storage if we're going to enable large-scale penetration of PV. And it's a big challenge. It's one where I think we have pretty good ideas of how to do storage on very short time scales. Seconds we can do for voltage regulation, for frequency regulation. I think we have technologies that will no doubt work okay for day-night storage. I don't think we have any particularly great ideas for seasonal storage yet. So that's one of the big agenda items for research to enable large-scale penetration of storage. Another issue is what happens to the grid as I put more and more distributed solar in the system. So much of the solar we've been deploying today in the U.S. Is residential scale. storage. In fact, most of the installations in the U.S. are residential, even though some 60% of the capacity that's been installed is utility scale. As we put more and more solar distributed around the system, we find needs to reinforce the system because the grid is not designed for two-way power flows. And so there's often need for reinforcements in the grid, which are the result of higher cost as I put more and more PV on the system. And then lastly, an example of things we need to do by way of policy to prepare for greater solar penetration is to rethink some of the policies that we use to incentivize solar installations. One of these is called net metering. If you're not familiar with net metering, it's a policy in which you charge a residential solar customer only for the net amount of electricity he or she consumes, right? What that means is that you're not paying for the wires that you're using to sell your excess electricity during the day or to buy back the net in the evening. So here's the way that works. Let's suppose a system in which there are no residential solar customers. Each customer is paying the utility for electricity in a number of buckets. At least one of those buckets is a wholesale energy price. That's the generator's price. And then there's an additional piece that's put onto that, which is associated with the network, getting the electricity from the generator to you. And so it's the sum of the energy cost and the network cost that results in the retail price that you pay as a customer. Your bill may look more complicated than this. Mine does, I can assure you. What happens when you use net metering as an incentive for residential solar is illustrated here, where we assume we have customer A who puts solar on her rooftop. And as a result, she gets paid by the utility for the solar she produces at retail rates, right? So that means that she's getting paid for the generation she does, which is what any generator, wholesale generator, gets. But she's also getting paid the transmission distribution cost for that. The other customers on the system continue to pay wholesale cost, the network cost, but they also have to pick up the cost, her share of the network cost, since she's not paying it anymore, right? So what's wrong with this system is that you will no doubt build up considerable consumer resistance to solar penetration by people who don't want to pay for somebody else's electricity. And I think we have to be sensitive to have systems that can scale up to large penetration of solar. So that's message two. The last message, and I just one or two slides here, is on the need to rethink how we support solar deployment at large scale, and how do we get the most solar for the dollar spent. And I think this is particularly important in the absence of a price on carbon, which we don't have now, and who knows whether or not we will get one anytime soon. So this is a look at how we do subsidy of solar installation today in the U.S. with the federal investment tax credit. And what you'll see here is that in a place like California, again, utility scale solar, which we saw earlier, is the most cost-effective solar you can do, the best resource for solar, and the best model for installing solar. You can see that it costs you about $110 per megawatt hour for installing that utility scale solar. You get a 30% investment tax credit on that, so you bring it down here to about 68. Okay. So the subsidy per megawatt hour is $37, right? On the other hand, for those of us who put in, I should say, for those who put in residential scale solar in a place like Massachusetts, it costs a lot more per megawatt hour. It's not a good solar resource, and it's an expensive way to install solar. So the cost is somewhere up here around $270 a megawatt hour, which gives you an ITC of about $107, right, per megawatt hour. So what you see is that we give more incentive to the least efficient solar, right? That's to the residential in Massachusetts as opposed to the utility in California. Why that's important is simply because we don't have infinite money. And if the goal here is to reduce CO2 emissions in our energy system, you'll want to get the most CO2 out of the system for every dollar you spend, right? And you won't get there this way, right? So a fix would be, if you don't have a price on carbon, a fix would be to move to a production tax credit, right? So you actually get a credit based on how much solar electricity you produce, not what it cost you to build the system. Better yet would be a price on carbon, and then let the market figure out what's the cheapest way to do this. So to summarize, the main messages here are first of all that we need to focus going forward on new transformative technologies that have the potential to reduce overall system cost. We've seen we've gotten pretty low in module cost today with silicon-based systems. Can we develop new systems that are both efficient and cheap to install? Right? Secondly, we've seen that we need to pay attention to enablers for large-scale penetration into the electricity system. A key issue there is storage, right? So how are we going to deal with intrinsic intermittency in solar power? For some period of time, decades, we can deal with that with integration with natural gas, right? But in the long term, we need to figure out how to do storage. And then lastly, we need to figure out how do we support this development and deployment of solar as economically as we can so that we get the most environmental benefit for the subsidy dollars that we spend. And that's this idea of production tax credits or a market with a carbon price. So with that, I'd like to stop and thank you for your attention and be happy to answer questions you might have.
And we do have time for questions from the audience.